Hello, everyone. My name is Abhinav Bhatele. I am a professor of computer science at the University of Maryland. And in this next portion of the hands-on tutorial on Python programming, we will talk about using Hatchet to identify different performance issues. Let's start with a recap of the Hatchet operations we have seen so far. Filter helps us subselect the data by filtering on the data frame. You can either use simple functions to filter the columns by, just like you do with the pandas filter, or you can use Hatchet's call path query language to specify call path patterns, and this can help us with doing more complex filtering. Squash is typically applied after a filter operation, and this helps us prune the graph once a data frame has been filtered based on some filter operations. The drop index levels function can be used to drop the multi-index in the Hatchet data frame, and this helps us aggregate data on each node of the call graph across ranks and or threads. We've also looked at different functions to add, subtract, multiply, or divide two graph frames, as opposed to a scalar addition or subtraction for all the nodes in a graph frame. This is actually a vector operation where we add or subtract corresponding nodes in two different graphs. Finally, the tree function in Hatchet helps us get a string representation of the graph, which a user can use to print the tree to stand it out. Okay, so let's now start looking at how can we compose these different operations together to identify some commonly occurring performance issues. What I'll do in this next part of the tutorial is use a Jupyter notebook to talk about the various operations. However, all the operations I talk about also are in the slide format. So if you want to later go back, you can look at the PDF slides that are in the tutorial materials. We will also provide the Jupyter notebook that I'm using here in this tutorial. So the first example we are going to look at is for generating a flat profile. Now, if you've used tools such as gprof, you might be used to looking at all the functions in my program and sorting them by time to see what functions does my program spend most of its time in. So the flat profile, so Hatchet helps us generate a flat profile with just a few lines of code. And this would have been difficult without a Python interface such as Hatchet if you were working with complex output from our HPC measurement tools such as Caliper or Timmery or HPC Toolkit. So let's see how what the code for this looks like. I'm going to try and annotate the slides to point to some of the important things we are discussing here. So first of all, we load in the data set. In this case, we are running a proxy application called cryptkey. We use the from HPC Toolkit function to load in the cryptkey data set on this line. Next, we drop the index levels in this data set such that the data is now aggregated over the MPI ranks. So each node has one time associated with it, which is the average amount of time spent in this node across all the ranks. Now, if we just wanted to see what are all the important functions in my program, we can do a group by on the data frame. The group by operation in pandas helps us aggregate multiple rows if they have the same value in a particular column. In this case, we are asking pandas to group the data frame on the name column. So all the functions that have the same name are going to get aggregated together into a single row, and we can specify the function we want to use for aggregation. In this case, we want to use the sum function. So this will aggregate the time spent in each function across all the invocations of those functions. Once we do that, we can then sort the data frame by the time column, and then we can display this sorted data frame. So in this line, we sort the data frame by time, and then we can use the display operation. Once we do that, as you can see here, we now have an output of the data frames sorted by time. So in the first column, we have the names of the different functions. And the second column tells me, since we filtered, since we sorted by the time column, it tells me the functions in which I spent the most exclusive time. So we can see here, this is Kripke, the next one is Kripke BGZ scattering, and so on. This can help you figure out what are the functions that are most important in terms of performance, and you can focus your optimization efforts on such functions. Now, one added benefit of having things in Hatchet, or having the data set in Hatchet, is you are not restricted to the name column, which is what some tools provide. You can now do a group by on any categorical column and look at results in different ways. So for example, if you wanted to do a group by on the load module, you can do that in Hatchet. And then you can say, I want to see what are the modules in which I spend most of my time. So you can see here, we have done a group by on the module. And just give me 1 second. So in this case, we are doing a group by on the module here. And once we do a group by, we are sorting again by time and looking at the values of the different load modules. So we can see here, we spend most of our time in the Kripke module, but there are some other modules that are also relevant. The lib monitor in HPC toolkit, libc here, libpsm, which is the communication layer for Intel machines. So using this, you can see what load modules do I spend most of my time in. Again, you can do this by other columns. So for example, if you want to do a group by on file, you can take a look at what files do I spend most of my time in. So it seems like we spend some time in the Kripke unknown file, memset.s, some malloc files, and so on. So the main idea that I want to get across with this one is that you can do group by on the data frame that is in Hatchet and look at the data in different ways, sort it and print it out to see where do I spend my time. The next function, or the next capability that we look at, is to identify load imbalance. So let's say we have a data set, in this case Lulesh, that we ran on 16 nodes or 512 cores, and we want to see what nodes in my call graph have the most load imbalance. And we measure load imbalance in this case by looking at the ratio of the max load to the average load. And if that is high, it suggests that some nodes, in some nodes, some MPI process spends a lot of time compared to the average time that should be spent in this node. So again, we start with loading the data set into Hatchet, which happens on this line. And in this case, this is a caliper data set. So we use the from caliper function to do the load. The next thing we want to do is look at the average time spent on a node, on each node in the call graph, and the max time spent in the same node across all the MPI ranks. To do this, we use the drop index level functions, but we apply it twice to do two different aggregations. So first, we make a copy of the graph frame on this line. So that's GF2. And then we use drop index levels both on GF1 and GF2. In the first case, we use the mean function to get the average time spent in each node of the tree. In the second case, we apply the max function to get the maximum time spent in each node of the tree. Now, once we have these two data frames, one with the average time spent in a node and the other with the max time spent on the node, you can guess that we can divide the corresponding rows of the data frame on the time column to look at the imbalance. So now what we do is, in this next line, which is the critical line in this operation, to get the imbalance factor for each node in the call graph, we take the data frame 2's time, which really is the max time spent in each node, and divide that by the time column of the first data frame, which is the average time spent in this node. And that gives us an imbalance number for each node in the call graph that will suggest the load imbalance on each node. We can again then sort the data frame by the imbalance column to identify the top nodes that have the largest imbalance, and we can then focus on optimizing our performance efforts accordingly. So if I go down here, you can see the data frame. This is sorted by the imbalance column, which is the last column here. You can see the most imbalance in this particular run of Lulesh is in Lagrange nodal. The next imbalance is in main, and so on. Now, this 2.5 imbalance suggests that the max time spent in this function compared to the average time is 2.5 times higher. So there seems to be significant load imbalance which we might want to correct for good performance. Okay. The next operation that we will look at is to compare two different data sets. We saw this in the previous hands-on session on Hatchet, where we can calculate speed up between two different executions. We'll see some similar operations here that help us compare different executions. In the first one, we'll see the use of the subtract operation or the diff operation or the minus operation in Hatchet, which can help us do a pairwise subtraction of times spent in the same node in the call graph across two different executions. So let's say we ran Lulesh on a single node of an HPC cluster. In the first case, we only used one core per node. And in the second case, we used all 27 or 27 of the total number of cores on that node. And we want to see, as I run in more cores, where does my time increase happen? Like, what are the nodes in which I now spend more time when I run on 27 cores as opposed to one core? In this case, we load in the data into Hatchet using the from caliper functions in these two lines. So there are two data sets. We load them into two different graph frames, GF1 and GF2. In both cases, we drop the per process data and do an aggregation, which is the mean over all the MPA processes. So I now have a call graph that says each node spends an average amount of time X in that node. We can then try to print the two trees, which are the two different executions, which is what happens in the next statement here. And if I look at the print outputs, this is what it looks like. So you can see this is the first tree, GF1's tree, and looks like I spend a lot of time in calc R glass control for LMs. If I look at the second tree, which is on 27 cores, again, I see I spent a lot of time, in fact, a lot more time in that function. But let's see what happens if I now do a diff between the two trees or the two graphs, which is what we do here. Graph frame 3 equals graph frame 2 minus graph frame 1. And then we try to print the tree. Now, what we see in this case, if I scroll further down, is I actually spend a lot of time in the time increment function when I run on a larger number of cores, even though I also spend significant time in calc R glass control for LMs. That's not the node where the maximum increase in time happens. So this kind of an operation can help us figure out, as I scale up and run on more cores or more processes, where do I spend more time as I scale up? You don't have to look at the tree necessarily when doing this operation, especially when you have a large calling context tree or a call graph. The tree output can become very dense and difficult to parse through manually. Similar to some of the previous examples, you can, since we did a diff operation and the difference in times was stored in GF3, the time column in GF3 is actually showing me the difference in times for each node. So if I sort the third graph frame by the time column and display that, I'll see what functions do I see the maximum increase in execution time. So we can see here that these are the functions where I have the largest increases. And again, since this is where I find the increases, these are probably the functions I want to focus on to improve my scaling performance. In the next example, we are looking at something very similar, but in this case, we will also highlight another useful operation in Hatchet, and how do you combine the filter operation with the diff operation to look at a subset of the data. So in this case, let's say we ran Lulesh on 27 cores and 512 cores. And now the 27 cores run was on a single node, but the 512 core run was on 16 nodes. And I want to see what are the differences in the communication or MPI time when I run on a single node versus lots of nodes, right? Similar to the previous example, we are going to load the two data sets into two different graph frames. We drop the index levels here for both graph frames. Now, in this case, since we only want to focus on MPI, we first filter the data frames by only looking at those nodes whose name starts with MPI. And once we do the filter operation, now since the filter does a squash by default, if you do not specify squash to be false, we store the output into two different squashed graph frames. So squash GF1 and squash GF2. We can now subtract these two new graph frames to get a third graph frame, which we call new GF here, which stores the difference in time when I scale from one node or 27 cores to 16 nodes or 512 cores. Similar to the previous example, if we now sort this new graph frame by the time column and display it, we can see what are the MPI functions where I spend more and more time as I run on a lot of cores. So if I scroll down a bit, you can see that this is the graph frame. It seems that we spend a lot of time in MPI all reduce when I run on 512 cores. The next one is MPI finalize, and then MPI send, and so on. So what this shows us is that you can combine multiple operations and compose them together. And if you wanted to look at a subset of the tree, you can first filter to identify a particular subset. And then you can do a diff operation if you're trying to compare two different executions and see where do you spend most of your time. In the final example in this session, I'll talk about a scaling study where we run an application on many different number of processes, and we want to compare their performance and see, as I scale my code, where do I spend a lot of time? In this case, we are looking at weak scaling, but you can do a similar analysis for strong scaling. And I want to point out here that this kind of analysis is really challenging to do with graphical user interfaces. Sometimes some interfaces allow you to compare two executions or three executions, but being able to compare many different executions is difficult with existing tools. And I think Hatchet does a great job with providing such capabilities through a programmable interface. So in this case, we ran Lulesh on many different core counts, 1, 27, 64, some cubic powers. And we have, I believe, 8 different data sets here. So the first thing we do is load all of these data sets into Hatchet. This represents all the different data sets we have. We use a for loop to create each individual graph frame from one data set that is stored into GF. In this case, we are going to look at where do I spend most of my time, or where do I spend significant amounts of time when I scale my problem. So here we are not going to look at the graph portion of the graph frame. What we do is we try to combine the data frames from all these different data sets together. So we first read in each individual data set in a for loop. We drop the index levels to get an aggregate time for each node. We then add a column to the data frame that can specify what was the number of processes I ran this particular data set on. This is going to be used to uniquely identify each particular data set, right? We also apply a filter in this case because we are only interested in the functions that we spend significant time in. So we filter where if the time is greater than this number, we keep the node, otherwise we remove the nodes. And then once we have done the filtering, we append this data frame into a larger data frame. So this data frames is where we are collecting all the individual data frames from the different data sets in this directory. Once we have done that, we can now move on to the next step where we want to look at the data by the number of processes. So there are a few handy operations in pandas which help us do this. First of all, we had a list of data frames that has all the individual data frames from the different data sets. We use the concat operation in pandas, which helps us combine all the data sets together into a single data frame. So the result is where we combine all these data sets together. Next, when we combine these data sets together, the combined data frame still has all the nodes as the index column. And there is an additional column now, which is called PEs, that tells you this node on these many processes has this much time, right? Since we want to look at data from the point of view of number of processes, we do a pivot operation. Again, this is a pandas operation on the resulting data frame, which says, I want the index to be the number of processes, and I want the different columns to be the names of the different nodes. So again, in the original data frame, the index was by the node, which is the default for Hatchet. But now we're going to make all the nodes the columns in the data frame, and the index will be the number of processes. And each column will store how much time do I spend in this particular node of the call graph for a particular number of processes. Once we have done this pivot operation, the next few steps are really straightforward. We can now plot the pivot function using matplotlib here. So we are going to use a stack bar plot to look at what functions are important as I scale up. So just to use my annotations again, one of the most important functions that we're using here is this pivot operation, where we are saying I want the number of processes to become the index and the columns to now be used from the names of the nodes. Once we do this plotting, and all of these are just to show a nice plot in matplotlib. Once we do this, we can now scroll down further and look at what plot is generated. And you can see the result here. On the x-axis is the number of processes, 1, 8, 125, 27, 216, and so on. The y-axis shows the time spent in different functions. So for example, the blue is calc energy for LMs, the orange is calc R-glass force for LMs, the green is calc R-glass control for LMs, and so on. So you can see, as we look at this, we can try to identify what functions do I spend more time in as I scale up. For example, some of these functions that are at the top do not exist in the single process run. Also, in some functions, such as this green one, I spend more time as I scale up to a larger number of processes. So this kind of function, or this kind of functionality in Hatchet, can help us identify what functions do I spend more time in as I scale to a larger number of processes. Again, you do not need to plot things necessarily. You can also look at the data frame and get the same information. So in this case, if we were to just look at the number of processes and if we just display the data frame, we would be able to see for each number of processes, what nodes do I spend my time in. Of course, you might have to do some sorting to figure out what are the nodes with the largest times, or what are the nodes where the time increases are the most. In summary, operations like this can help you identify scaling problems or scaling issues in your code by helping a user identify, as I run on more number of processes, what functions does my time increase happen most in? And that can help us focus on certain functions of the code. So that brings me to the end of this part of the hands-on session. I hope you find these examples using Hatchet useful. There are many, many different ways of composing Hatchet operations together. We cannot exhaustively cover all of them. It depends on the specific use case, the kinds of issues you're trying to look for, and the kinds of problems you want to identify. I'll stop here. Thank you.